Hello and welcome to the Chapter 5 podcast in Section 5.2. Today we're going to be discussing the first law of thermodynamics. Internal energy is the sum of the kinetic and potential energies for everything that shows up within a system. Different systems will have different components, and the values of kinetic potential energies will vary depending upon what the actual system is. The first law of dynamics is very similar to the law of conservation of of mass, in the sense that energy is conserved. So energy is neither created nor destroyed, it can just change form. E is the variable that we'll use, and it stands for internal energy. The change in E represents the change in internal energy of the system. The change in internal energy is the final energy minus the initial energy, so it's the difference. And it's a number, a unit of measure, and a plus or minus sign. So remember, if it's negative, it's leaving the system. If it's positive, it's being added to the system. And here are some examples that kind of show different ways to show whether energy is lost or energy is gained by the surroundings, and what happens to the initial and final state. And then this is a more specific example. So this is a reaction, and depending on what direction the reaction is going, you can see that the change in energies sign will be equal and opposite to each other. So how to relate this to heat and work? Internal energy is a function of heat and work, so delta E, the change in energy, is equal to Q plus W. When heat is added to a system, or when work is done on a system, the internal energy increases. Now remember, if this happens, that means that we're adding energy to the system if either of these two situations happens. Okay? When energy is transferred from the system to the surroundings, Q is positive. When work is done on the system by the surroundings, W is positive. Okay, so keep that in mind. I know it's kind of hard to keep track, but if you ever get confused, think about this table here, because it'll help you keep track what the values are in terms of whether they're positive or negative. Okay, usually students who make these mistakes with these kind of problems, it isn't because the math is hard, it's because they get the signs backwards. So it's important to kind of keep this in mind, and with enough work, hopefully, and practice, this will begin to make a little bit more sense. Here's an example of a heat and work calculation. So let's say we are calculating the change in internal energy of a system where the system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. So Q is negative 85 because the system is doing the work. So when the system is doing the work, that's energy that's leaving the system. So that's why it's negative. And 140 represents it's going into the system, so it's going to be a positive value. And when we look at the change in internal energy, we just sum these values, and so the sum is the difference between these two numbers, which is 55 joules. And again, as you can see, the math isn't difficult, but it's just a matter of defining the sign conventions properly. Exo and endothermic processes. An endothermic process is a process in which heat is absorbed by the system. So heat is flowing into the system, and it's associated with increases in temperature. So for instance, I purposely put this picture of melting ice on here to kind of illustrate that. So if we define the ice cubes as the system, the heat is flowing into the ice cubes, and as a result, the temperature increases, which causes the ice to go from the solid to the liquid state. Exothermic processes are systems is a process where heat is lost by the system. So heat is flowing out of the system, and the temperature will decrease as this continues. So if this is, something on fire, the heat is leaving the system if this little burning thing represents our system itself. State functions. State functions basically is specifying the current state of the system. So in other words, what's its temperature, pressure, location, and so on. Values of state functions only depend upon what the system is at that moment. It does not matter how the system got there. Okay, internal energy is a state function. So what I mean by that is this. If we have a 50 grams sample of water at 25 degrees, all that matters is that this is a state function in the sense that this is what matters. It doesn't make a difference whether we had hot water that we cooled to get to this condition or whether we have cold ice that we had to heat to get this condition. The state doesn't differentiate between in the path in which we got there. It may not seem like a big deal now, but later on it may make a difference. While internal energy, delta E, is not a state function, Q and W are not state functions. Okay, so in other words, the values of Q and W depend on what happens. Okay, so even though the total delta E is a state function, how Q and W are defined make a difference. So in this particular example, if we have a heating coil and the battery powers the heating of this coil, here it's all Q, or all heat. Whereas if we have the same exact battery system and we're powering a fan instead of a heat coil, now even though the delta E is the same, the energy lost by the battery is the same, the Q and the W will not be the same as in condition A. So while the delta E, the internal energy, is a state function, Q and W aren't. So in other words, it makes a difference. The energy change doesn't make a difference in the sense that the batteries are both losing the same amount of energy, but how the energy is used is different, and that's what makes Q and W special. And that is it for now.